Hi everyone, we JQ, Jabir, Natalie and Razlan have conducted the Pendulum Bob Experiment. We will connect our experiment to our topic, trigonometric function. We choose to conduct this experiment because it is one of the simplest experiments to conduct. And most importantly, the concept of pendulum are used in various ways in our daily lives. For instance, pendulum can be found in grandfather's clock, swing, amusement park rides. It can also act as a tool to receive earthquake and wind in skyscraper around the world. All these to help improve our lives. Firstly, we hypothesize that the velocity of the bob over time it looks like a sinusoidal graph, and we also predict that as the length of the string increase, the sinusoidal graph will be less steeper.
So, in order to conduct our experiment, we need a pair of scissors, 10 cm, 20 cm and 30 cm string, a marker pen, a 100-gram bob, a vernier calipers, a string roller, a retort stand, an electronic balance, stopwatch, a meter ruler and an iPad. We then place a meter ruler beside the retort stand to allow the capturing of the height of the bob when swinging left to right. This will give the maximum and minimum of the graph later on. After that, we tie the 10 cm string into the string roller attached to the vernier calipers with the bob at the end. We then swing the bob and start the stopwatch at the same time as an indication to stop the bob at 6 seconds. When the bob started swinging from left to right, we capture the swing of the pendulum bob by using an app on the iPad called Video Physics. We repeat this experiment for 20 cm and 30 cm string respectively.
The swinging of the bob from the left to the right gives us a graph that looks like a sinusoidal. This is because when the bob swings away from the equilibrium position, the velocity decreases, and when the bob swings closer to the equilibrium position, the velocity increases. The swinging of the bob from the left to the right gives us a graph that looks like a sinusoidal. In addition, we realize that the maximum velocity for all three graphs is the same for 0 to 6 seconds. The maximum velocity remains constant at 2 cm over second. However, the maximum velocity for all three graphs will eventually change as the swing of the bob will slow down as time increases. We do not know the exact time it will stop as we did not measure it, but we know that the velocity of the bob will decrease until the bob stops.
Furthermore, we realize that the steepness of the graph varies with the different length of string used. The shorter the length of the string, the steeper the graph will be. This is because time taken to complete one oscillation will be faster for shorter string than longer string. For instance, the graph of the 10 cm string is the steepest and the graph of the 30 cm string is the least steepest among the three different lengths. This is evident as the average velocity of 10 cm pendulum bob is the highest and the average velocity of 30 cm pendulum bob is the lowest. Moreover, the instantaneous rate of change of velocity at 0.5 seconds of the 10 cm pendulum bob is the highest, and the instantaneous rate of change of velocity at 0.5 seconds of the 30 cm pendulum bob is the lowest. Therefore, we can conclude that as the length of the string increases, the less steeper the sinusoidal graph will be. Hence, our hypothesis is accepted.
The pendulum bob experiment can be seen almost in the things we observe or use, how it improves our society. The trapeze artist in a circus, for instance, is a great example of our experiment. The longer the string used by the trapeze artist to swing in the air, the slower he or she will swing one complete oscillation from left to right, and thus it slowed down his or her ability to perform stunts in the air. Apart from that, engineers who build swings in the playground have to measure the ideal length for the swing. Shorter swings might cause the swings to oscillate faster, hence greater velocity and vice versa. Therefore, engineers play a pivotal role in ensuring children's safety while playing on a swing.
Pendulums are used in the advancement of technology to improve our lives. It is used in skyscrapers to resist earthquakes. For example, engineers have built a quake damping pendulum on the top of Shinjuku building in Tokyo. This technology is very useful as Japan often experiences earthquakes. So, when an earthquake begins, it pushes the base of a tall building in the direction of the seismic activity. The top of the building is left motionless for a moment, but then soon catches up. But by then, the bottom has moved back in the opposite direction. Such motions causes tall buildings to sway violently, resulting in damage or even destruction of the building. Therefore, pendulums are installed on the upper floors to counter such motion in skyscrapers. They work by automatically swinging counter to the motion created by the earthquake. As a result, a reduction in swaying and hopefully reduce the risk of harm to the building and the people in it. On the other hand, engineers have to ensure the length of the cables used in the pendulum is an ideal length for an optimum function during an earthquake. Longer lengths of cables may cause the pendulum to sway slower, lower velocity, while shorter lengths of cables cause the pendulum to sway faster, higher velocity. This is because the pendulum in skyscrapers are not meant to sway too fast or too slow.
Similarly to the damper used as an anti-earthquake technology in Japan, it is also used on skyscrapers to counteract winds, reducing the building's sway and keeping motion sickness at bay. Taiwan, sitting just 660 feet from a major fault line, its tallest skyscraper Taipei 101, is prone to earthquakes and fierce winds. Hence, engineers built a tuned mass damper, a 300-ton pendulum on the skyscraper to achieve stability and lessen the impact of violent motion. When the building sways in a gust, the heavy 300-ton pendulum weight inertia acts as a counterweight, pulling it in the opposite direction. Just like the one in Japan, engineers have to determine the length of the cables holding the pendulum for optimum function when the pendulum sways left to right during a wind attack or an earthquake. This is because the force of wind against buildings can cause the top of skyscrapers to move more than a meter and can cause motion sickness in people. Typically, skyscraper must be flexible in strong winds yet remain rigid enough to prevent large sideways movement. Without a doubt, this technology has helped us build even greater and taller skyscrapers as land becomes scarce in the future to come. In fact, this technology is widely used on skyscrapers in Canada, Dubai, China, Japan, USA, and Germany. To conclude, pendulums is inevitably a great invention by Galileo Galilei, as it is used in various technologies to help improve our lives. After conducting this experiment, we have learned the importance of teamwork and communication. We have definitely grown a great sense of these skills which we will need in our future. Thank you for watching.